So last time we introduced the concept of mutual independence and dependency diagram and this local lemma. We also learned about symmetric local lemma, and this is more general version, general local lemma. In short, dependency diagram is that you have a vertices which corresponds to the events that you want to avoid. These are bad events, and there are these vertices which are, let's just write it. The vertices are the indices which corresponds to the bad events that you want to avoid. And in here we have a dependency diagram. So one has neighbors 2 and 4. That means that the A1 is mutually independent to all events where this I is not in the our neighbor. So this events A1 might depend on A4 and A2, but the rest of them, whatever happens in here, does not affect the event A1 at all. So that's captured in this dependency diagram. And if we know that this dependency diagram is there, and then we have these events, and somehow this dependency diagram is weak. This dependency is weak in terms of that there exists real number x1 to xn, such that each probability AI, each event AI happens with a probability bounded by this number. So here, if this dependency diagram, the degree of I is small, then this becomes not too small. And on the other hand, if this set has a big size, then it tends to be a big number. So it's more difficult to satisfy this. Anyway, as long as this holds, then we can actually lower bound the probability that none of the bad events happen. So we can actually, with positive probability, we can actually avoid all the bad events. So this shows the existence of way to actually avoid all the bad events. That's what we wanted. So now we want to prove this. So we first want to use induction on S to show that the following holds. For any S of size S strictly bigger than smaller than n, and an index I in which does not lie in S, we have the probability that AI happens when we assume that none of the events in this S happen is at most xi. So this kind of shows that what's our plan of showing this. So probability of none of the event happens can be written as probability that the AI does not happen when J is everything but I, none of them happens. And you can keep writing this in terms of multiplying more. So this times probability that the A, say I prime, also not happen when all of the other events shall not happen. You keep multiply this. You shrink this index set one by one, and then you take out, and then you multiply this, then that's our probability. And we want to show that each of them has probability at least 1 minus xi. Then you get this inequality. For that, if you flip this into original one, this being at least 1 minus xi is same as this being at most xi. So our plan is to prove this and then use this to prove this desired inequality. So how do we prove this? Is using the induction on the size of this set S. So this is small s, and this is capital S. And this is true if S is 0. So assume, as we are using induction, this holds for all S prime smaller than S. So now we have this, we want to, bound the probability of this AI happens depending on this S. S and I are there. And as we know that the I is, depending on the events on this out neighbor, on the other hand, outside of here, whatever happens inside of here does not really affect the probability of AI. So we want to first divide this S into two, S1 and S2, S1 which lies inside of the out neighbor of I, S2 which does not lie in there. So let S1 be the indices which corresponds to the event which AI actually depends, and S2 be the rest. Then what's the probability that we want to estimate is when all the events in S are not happened, conditioning on that, what's the probability that AI happened? So we know that the conditional probability, this is same as let's say this over, let's copy here. So these two are the same. And this part can be written in the same way. Let's say for S1 you do this, and for S2 you also measure the probability that it doesn't happen. Then AI, say S1, S2. So we did nothing but just rewrite this. And so this probability is nothing but that this is, so let's say this is C, this is D, then probability that C and D both happen is same as the probability that C happens when D happen and probability that when D happen. So this is D, this is C prime. By applying this to both of them, so above one is, this times 2, and the below one is probability that C prime D times probability D. So this cancels out. So remaining one, you can just write the XAI, and when all the events in S1 happen, and when all the events in S2, we assume that this happened, and then we found the probability that all of them happen. So we can rewrite this in this way. So now we can rewrite this way because whatever happened here is, AI is not, AI is independent of whatever happens here. So we write in this way later so that we can actually exploit the assumption that AI is not depending on any events there. So now we want to measure this enumerator and denominator, and we want to estimate that so that we can bound this probability. First, what's the numerator? AI, and what happens outside of S1, and what happens in S2. We have that this event is smaller than AI itself, so we can just forget whatever happens in S1. Then this holds, and then this is actually same as AI, because AI is independent of whatever happens outside of S1. So this is what we have. And by our assumption, this probability is at most this xi times the x1 minus xj, where j is the out neighbor of I in the dependency diagram. So this provides the upper bound for the numerator. And for denominator, here we want to now use the induction hypothesis to bound it from below. So if S1 is empty set, then this is just 0. No, denominator is 1. Otherwise, let S1 be the J1, J2 to JR. Let's say there are R of them. Then what's the probability that we want to measure? Because of J, it's a bit confusing. Let's write L here. Then this is nothing but the probability that a J1 doesn't happen, assuming conditioning on this times probability that a J2 does not happen, conditioning on all previous one. So conditioning on this, and you compute the probability that AJ1 doesn't happen, and assuming that all of this does not happen, so all AL doesn't happen for L inside of S2, and in addition A sub J1 doesn't happen, and then you compute the probability that AJ2 doesn't happen, probability that the AJ3 doesn't happen, assuming that the S2 together with J1 and J2 doesn't happen, and so on until you multiply the last term. AJR does not happen when L is S2 and J1 to JR minus 1 does not happen. So this is equality. And each of these are nothing but the 1 minus probability that AJ1 happen when this doesn't happen. So you can actually flip. So these are the complement events of AJ. So you can actually write it as 1 minus the not complement event. And so on. And by the induction hypothesis, what was our induction hypothesis? Induction hypothesis is that for any I and S of size strictly less than S, we have this inequality. When assuming the events inside of S, none of them is happening, the probability that AI happens is strictly, it's at most Xi. So each of these is at most Xi. Because now S2 has a strictly smaller size because we assume S1 is non-empty. So S2 has a size strictly smaller than S. Not only that, this set also has size strictly smaller than S, because this one event is kicked out from S, then that's exactly what we have here. So now, because our induction hypothesis, then this is nothing but the multiplication of J sub S, where S is 1 to R. This is not good notation because of the S before, so we have, what can we write? Say L, J sub L. Then, of course, this is lower bounded by taking all, out neighbor of I, and then just subtract x, multiply 1 minus xj. So you have this as a lower bound for the denominator, and for the upper bound we have this. So by using this and that, we can actually bound this. This is at most the first one divided by the second one. So this is second one, this is first one. Then this concludes that the probability that AI happens when all the events corresponding to S does not happen is at most xi. So this proves our claim. What was our claim? This claim. So by using this claim, now we can prove that the probability of none of the bad events happen is actually 1 minus probability that A1 happen. So this is probability that A1 does not happen, times 1 minus probability that A2 happen when A1 does not happen. So this is the probability that when A1 doesn't happen, A2 doesn't happen. So conditioning on A1 not happening, this measures the probability that A2 not happen. So we keep multiply this up until to the nth one. And by the claim that we just proved, this is lower bounded from the multiplication of 1 minus xi for all I. So this proves the general version of local lemma. And using that, we can also symmetric version. That it says that when we have a A1 to AN be the events such that each is mutually independent of all but and most the other events. So in other words, the dependency diagram has an out degree at most d. If the probability of each event happening is bounded by p for all I, and E times P times D is smaller than 1, then probability that none of the event happen is positive. So now, this is a corollary for the general version. And if D is 0, then this statement is trivial. So we assume D is, strictly bigger than 0. Because if D is 0, that means these events are all independent each other. So this probability is, you just multiply the probability, 1 minus P, all of them, then that's a lower bound. And of course, we have to assume that P is smaller than 1. Okay, so what we do is we take xi be 1 over t plus 1 which is smaller than 1, for all I. Then what do we have? Then we have 1 minus 1 over d plus 1 to the d is actually at least 1 over e for any d. So this guarantees the condition here. So this is m of p, and this part become 1 over e, and this part 1 over d plus 1. Because PED is smaller than 1. Give me a moment. What did I write wrong? Let me check. Okay, so let's write this way. So P times E times D plus 1 is smaller than 1. Then, yeah, so let's say this is the condition. Then, so because of that condition, we have actually inequality here. And then we know that this part is, at least 1 over e times 1 over t plus 1. So this condition for general version of local lemma holds as long as we have these. So you apply that, then you get the, you get the conclusion. So here, if you see, the crucial point of the dependency diagram that we use is this inequality, this equality. This is where we used. And for this proof to work, this doesn't have to be really equality. As long as this is inequality, this also holds. And also, yeah, even if this is inequality, we also hold, this also holds. Or even, as long as we have a comparison this with these two, with this inequality, that also holds. So later we can actually prove, we can actually use a stronger version of local lemma, where we don't really have to have this equality. Instead of the dependency diagram, we can actually consider a negative dependency diagram, which doesn't give the equality, but which may give the inequality. But anyway, that's where we're gonna get to that when we actually encounter that example. So maybe in the next lecture or next lecture, maybe probably next lecture, we will talk about that. So anyway, keep that in mind, that in the proof, this doesn't have to be really equality for the proof to work. So now we have collected this local lemma. So now we will see some example of how we can apply this to some other problems.